Welcome back to the channel. I'm Daniel with CMC Learning, and today we're going to look at some more PAT questions, so the Physics Aptitude Test for Oxford Physics. And today we're going to be looking at some of the sort of earlier questions in a paper. Here we've got a Physics 2022 paper, and really what we want to look at today is some of these sort of easier marks to pick up, and really the best way to do all of these problems. So we'll be looking at mainly the mathematical ones. We've got a few problems here that we're going to look at. And we might as well get started here with the second question on this paper, which is asking us to find values of x for which this sort of function over here is positive. So just by looking at this, looking at the answers that they give us, they're giving us sort of ranges for values of x. Some of these will probably make them positive, some will make them negative. Only way to find out is to do some operations on this expression. So the first thing we should probably take note of is this power of minus 1. So this is sort of index laws 101. If we have some expression in brackets and we put a power of minus 1 there, we can write that expression as 1 over the entire thing. Also, what I'm going to do in this step is just make it a little bit simpler. I'm going to order my terms in sort of descending order of powers of x. So what this gives me is minus 3x squared minus 14x plus 24. This will be the first step here. And hopefully what we can see here is certain values of x are going to influence what this denominator becomes. And they want us to say when this expression is positive. So another way of putting that is when this entire fraction is greater than 0. Now if we have a look at the numerator on our fraction, we have a positive number. The denominator is going to be any number depending on sort of the values of x that it can take. In order to get this fraction to be greater than 0, we need the denominator to also be positive. So in a way, we need to solve some expression where all of this denominator is positive. So let's have a look at how we can do that. Obviously, we could try and sort of factorize this expression, see where it takes us. We need to be left with some inequality. So let's write that out as the next step. Here we need to solve when minus 3x squared minus 14x plus 24 when this number down here is greater than 0. Okay. Now there are a few sort of simplifying steps that we should take. Just by looking at this, this is quite a nasty polynomial, especially given that this question is 2 marks. We don't really want to be faffing around with prefactors and whatnot. So what we should do here is take out a factor of minus 3 from each of these terms. And we'll see how this changes our answer. So here we get x squared. We get x squared. This minus 14 goes to a plus 14 over 3. So we're taking out a factor of 3, more specifically minus 3. And this negative 20, or this positive 24, sorry, goes to negative 8. And all of this needs to be greater than 0. Now something has changed here. Here we can take out this sort of power of minus 3 here. Or sorry, this bracket, this factor of minus 3. And we can see that for this condition to be satisfied, for this expression to be greater than 0, we've now sort of created a sub-expression. And that is when everything inside of these brackets is less than 0. So it's almost a bit counterintuitive. We've now flipped the problem. And a good way to think about that is, in maths, whenever you're working with inequalities, if I divide by minus 3 on both sides, that would sort of flip this inequality over here. So that's a property of inequalities. And I guess the sort of quote-unquote proof is shown here. Essentially from this, we have a new expression. We need to solve when x squared plus 14 over 3x minus 8 is now less than 0. And you can get to this step from sort of logical intuition or just dividing by negative 3 on both sides. Okay. And typically, the way you'd solve most polynomials is try and factorize them into two expressions. Here we should probably complete the square because this x to the power of 1 term is fractional. It's going to be quite tricky to figure out what terms sum to make 14 over 3. So let's proceed with that. The steps for completing the square should be quite familiar by now. We essentially just half this sort of x to the power of 1 term. Do all of this to the power of 2, and then to sort of compensate for that, we need to take away this number over here squared. So minus 49 over 3, oh, over 9, sorry. Over 9, and all of this is minus 8. Keep in mind that this is still sort of less than 0. So we can simplify this expression here. X plus 7 over 3 squared minus 49 over 9 minus 8. You are allowed a calculator in the physics aptitude test, so it's sort of just worth it popping that in the calculator, saving a few seconds. Here we should end up with minus 121 over 9, and all of this needs to be less than 0. Okay, so we're off to a good start. Hopefully what we've seen here, we have some polynomial over here, and we need to show when that is less than 0. A good way to do that is sort of graphical methods. So I could plot on some axes. Essentially, my expression for x squared. We have a polynomial here. We have a sort of negative 8 y-intercept. And we have this positive term here. Oh. We can even sort of tell where the turning point is just by completing the square. So I know the turning point is minus 7 over 3 and in the x-coordinate, and then minus 121 over 9. So my turning point is going to be somewhere here with my sort of minus 8 y-intercept. Of course, this is not really to scale. And we need to see when this function is less than 0. And the reason we do stuff graphically, or a question like this graphically, it's really easy to see when this expression over here is less than 0. In this case, we've sort of just set this equal to y. And by doing so, we can see that when y is negative, our expression should be less than 0. So really, this is the region of x values. Mind you, I should put some labels on these x's. That's our range of x values there, sort of at these boundaries here, that give us negative values of our polynomial above. So we need to solve essentially for these roots. And if we're doing that by completing the square, the process isn't too tricky. Essentially, we just need to say when the polynomial is equal to 0. So to put that out a bit sort of nicer, try that somewhat nicer, we are saying y is equal to, here we have x plus 7 over 3 all squared minus 121 over 9, and we want to know when sort of y is equal to 0, what we get. So here we're sort of talking through the steps quite nicely, I think, because there's plenty of time to think. So if we were to solve this, there is a sort of trick that we should, or something that we should sort of respect in the mathematics. If we sort of move this 121 over 9 to the other side of the equation, take it away, or sorry, add it to both sides, we're left with this. And from here we need to be careful. When we do the square root of both of these terms, this is where we introduce a plus or minus. So you're probably familiar with that quadratic expression. When we're doing the square root of something, we do need to keep in mind that this introduces that plus or minus. So here we should have plus or minus, and we're doing the square root of 121 over 9. These are two nice square numbers. So this is 11 over 3. And this is going to be equal to x plus 7 over 3. Just like this, we essentially have two equations. I think it would help to write this out as two equations. We have x plus 7 over 3 is equal to, here we'll do positive 11 over 3, and here we have x plus 7 over 3 is equal to negative 11 over 3. From here we should be able to say what our value of x is, simply just by moving that fraction to the other side, or adding or subtracting this factor. So for our top solution, here we get 4 over 3. So positive, so 11 minus 7. On the bottom we're doing minus 11, top of that minus 7. So that gives us minus 18 over 3, which is the same as minus 6. So we can go up to our diagram, and we know that our roots are minus 6 and 4 over 3. Positive 4 over 3. If we have a look, just sort of recontextualize what we've done here. Essentially, we figured out when this expression over here is negative, which in turn makes the denominator of sort of our expression up here, makes that denominator, in this case, positive, so our whole fraction becomes positive because we have a positive numerator as well. So let's have a look. We have essentially our x value. We can write this as just one inequality. We can write this as x being greater than minus 6 and x being less than 4 over 3. If we have a look at the possible answers, we see that D matches up quite nicely with our answer. So in this case, D would be the answer to this question. And this was sort of merely through, I guess you could say, graphical methods. I think it would definitely be a process of trying to figure out maybe the roots of this expression. If anything, we're not really looking, like I said, for those roots. We're looking for when the denominator is either positive or negative. You could obviously complete the square with this factor of minus 3 there. I believe that just sort of introduces a bit more sort of negative numbers, more room for error, essentially. So that was question 2. And on the very same problem, or on the very same paper, sorry, just 2 questions later, we have another mathematical question. And again, for 2 marks, they really sort of want you to think sort of quickly, or use methods that are maybe unorthodox but get you the answer the correct way. They want us to say which of these polynomial functions has the largest second derivative at x is equal to 0. They've given us a sort of litany of functions over here. We have some powers of 5, 3, 4, 2, 1, 6 even, just sort of a list, a string of powers in this case. Before even sort of differentiating all functions, which I think is the naive option, essentially going one by one, subbing in x is equal to 0, and then seeing what that value is. Let's try and think sort of ahead a little bit. So let's have a look. They want to know what the second derivative is, but at a very specific value. This value of x is equal to 0. Let's keep in mind how we do polynomial derivatives. So for example, x to the power of n. If I do this first derivative, I should get n multiplied by x multiplied by, to the power of n minus 1. And doing that second derivative, I should get n multiplied by n minus 1, x to the power of, in this case, n minus 2. So we're just bringing down factors, or we're just bringing down that power and taking one away each time. So having a look at all of these expressions and keeping in mind that we're looking at the second derivative when x is equal to 0, if I look at this x to the 5 term, for example, my first derivative, in this case, is going to give me 25 x to the 4, and my second derivative is going to give me 100 x to the power of 3. But when we do sort of x is equal to 0, that x to the 5 term completely disappears. The same can be said for an x to the 3 term and an x to the 4 term. The key thing is, when we do the second derivative, essentially if we keep in mind what values we're looking at, if n is equal to 2, what I'm left with is this factor of, when n is equal to 2, my polynomial term disappears. I'm left with 2 multiplied by 1, in which case I'm just left with a factor of 2 multiplied by the x term, which would go to 1. So we can put that as 1. So this would have been our x term. And the same goes for terms where n is less than 2. So we looked at n greater than 2. That would just give us 0 when x is equal to 0. For terms less than 2, the first derivative is always already going to turn that into a constant. If we do the second derivative, that constant is going to go to 0. So what we should be looking at in each of these options here are these powers of 2. For example, x squared. A doesn't have an x squared term, so we can ignore that. B has an x squared term, C has an x squared term, D has a 2x squared term, and E does not have an x squared term. I can make sort of a little table over here of B, C, and D. I can take the second derivative of these terms just to sort of be sure. And I should be left with 2 for B, so an answer independent of x. For C, I should also be left with 2. But for D, in this case, this factor of 2, it sort of helps us greatly. In this case, we're left with 4 as the value for the second derivative of D. And of course, sort of these values here will be independent of any value of x. So the x squared term will always reduce to 2, 2, and 4. But it's important because they're telling us when x is equal to 0. Essentially what that means is all other terms will go to 0. So here the answer will be D. It's these sorts of maths questions which the PAT is sort of really made for. They want to find students who can maybe not take the obvious route, but take the easier / quickest route. And that is essentially what makes a good physicist, in my opinion. So yeah, I hope these two problems helped somewhat. These are sort of the easier marks to pick up on the PAT. It's definitely good to nail these because then it gives you more time on the physics questions on this exam, which obviously take a bit more thinking. If you liked the video, do be sure to give it a like, subscribe for some more aptitude test questions, maths and physics, and even some A-level and GCSE content. I'll see you guys in the next video.